Alright guys, let's go ahead and work through the problems in 705 projectile motion review. Question number 1 says, below, cannonballs are being shot straight horizontally at the velocity shown. If they come out of the cannon at the height shown, in what order will they hit the ground? And there are 4 of them here, A, B, C, and D. And in order for us to answer this, we need to solve for each of these, and then we can select which one was the least time, most time, and then farthest, shortest. There is spots here in case 2 are equal to each other as well. So looking at this, in terms of the time that a projectile is in the air, when you have something launched horizontally, the only variable that determines your air time is your height. Okay, because the horizontal velocity that it's initially launched at has no effect whatsoever on the vertical motion. Remember, horizontal and vertical motion are separate. They're independent of one another. So if I want to find the time, all I need to do is look at these heights, and the greatest height is at B, therefore it will have the most air time. And then we have A, and then we have C, and then we have D. And so we actually don't have to do any math to answer the first part of this question. However, in order for us to answer the second part of the question, we do need to do math. And so in order for us to know which one went farthest and which went shortest and everything in between, we're going to need to solve this for each one, looking for the range. So let's go ahead and start with A. And so for cannonball A, again, I'm going to be looking at the different variables for projectile motion, which is going to be initial velocity, final velocity, acceleration, time, and displacement. And I need to look at these separately in the x direction and in the y direction. And so I'm going to make myself a table similar to the ones that we made in class, and I'm going to fill it in for projectile A. And I'm going to do the same thing for B, C, and D, and ultimately what I'm looking for is this, the horizontal displacement. That's what we're going to be ranking. So for projectile A, my initial velocity in the x direction, that's horizontal, is the one in the picture, 18 meters per second. It's also my final velocity horizontally, because horizontally I don't have any acceleration. In the y direction, my initial velocity, anytime you have a horizontal launch, your initial vertical velocity is 0. My acceleration is due to gravity, therefore it's negative 9.8 meters per second squared. And let's see. And my displacement vertically is the height that's given in the image. And so this is 33 meters above the ground, therefore it will fall 33 meters, and so the displacement in the y direction will be negative 33. Okay, so in order for me to actually solve for the range, I have to get the time first. I can't do any solutions with my data in the x direction unless I know 2 of 3 things. I have to know velocity, displacement, and time, 2 of the 3. Right now I only know 1 of those 3, so I need to find time first, and we're going to do that using the vertical data instead of the horizontal data. And by the way, this process we're going to repeat for each of these cannonballs. So if I'm going to solve for my time, I have VI, A, and delta X. The equation we're going to be using to do this is this equation right here. Delta Y equals VIT plus 1/2 AT squared. It's one of our kinematic equations, and it's the one that has VI, A, delta X, and T in it, so it's the one that we need to use. Again, I wrote delta Y because it's displacement in the Y direction. Your equation sheet and the board say delta X, but you can use it interchangeably depending on if we're solving for X or Y. Alright, so my displacement vertically is negative 33. My initial velocity vertically is 0, so this whole bit's going to go away. I'm not going to bother even writing it because I'm going to be adding 0. And so I have 1/2 negative 9.8 t squared. Okay, so from here I'm going to divide both sides. Half of negative 9.8 is negative 4.9. that's going to cancel all of that, leaving me with t squared equals, and then I need to go ahead and divide these. The negatives are going to cancel. 33 divided by 4.9 gives me 6.735 equals t squared. And this is rounded. The full value looks like that. But I'm trying to solve for t, not t squared. So we want to go ahead and we're going to take the square root of both sides. Okay, and so square root of this value gives me my answer of 2.595. I'm going to call that 2.6 seconds. But again, this is not our answer. This is the air time. Time isn't horizontal or vertical, so I get to write that on both sides. And now I can use this to find this. Okay, now in the x direction, because my acceleration is 0, I'm going to use my constant velocity equation, which kind of looks like the last kinematic equation that we have up on the board. It looks like this one, delta x equals VF plus VI divided by 2 times t. Now because my final and initial velocities are the same because it's constant, this is just velocity because 18 plus 18 divided by 2 is of course 18. So you can just write it like this if you like, because that's what we're doing when we have constant velocity. Now if you do have different velocities, yes, you need to do this to get the average. Okay, and vertically you would want that, but horizontally it looks like this. And so if I want to solve for my displacement horizontally, that value right there, I'm simply going to be multiplying my velocity, which is 18, times my time, which we just found to be about 2.6. So in my calculator, I'm going to take my answer, I'm going to multiply it by 18, and that is the range for the first projectile for A. So whenever I compare them, this is the value I'm going to want to compare. 46.7. Okay, so we're going to do the same process for B, C, and D. And it's going to look pretty much exactly the same as it did for this one. I'm going to do that real quick on my own, and then I'll come back and talk about the ranking. So after going through and solving for each of these, I have these values right here. You saw me solve for A, but it was the same process for B, C, and D. I found the time using the vertical data, and then I multiplied that time by the velocity in the image for each, and these are my different ranges. So if I go down here to the bottom, the farthest range is going to be C, 60.4. Which again, if you look at it, it makes sense because it's pretty high off the ground. 31 meters is definitely not the highest, but this velocity, 24, is going to carry it farther forward than these that are taller. And so my farthest is going to be C, which is going to be greater than. The next farthest is going to be D, which was the fastest. However, it was also the closest to the ground. The next farthest is going to be A, and D and A were pretty close to each other because again, this one's a lot taller, but it's also quite a bit slower. And then the shortest range is going to be B, and again, if you look at the numbers there, that one's only fired at 12 meters per second. Least time. Did I put this in most to least? I did. I put this in backwards at the top. I apologize, guys. This is least time to most time, and I apparently did not read that very carefully. You can rank them, but you got to read it carefully. So, of course, the least time is the one closest to the ground. I have this exactly backwards. That's going to be D, and then C. We're going to flip this, and then A, and then B. There we go. All right. Luckily, we're on a review, so if you miss it like that on the first try, you do get full credit on subsequent attempts. Of course, if you miss it twice, you're going to have to get a similar question. Okay, question number 2. Question number 2 says, a ball is struck at t equals 0 seconds and follows the parabolic path shown in the diagram above. The following graphs show quantities possibly associated with the motion as a function of time, t. Assume that air resistance is negligible and that the positive directions are upward and to the right. Which graph represents the horizontal component of the velocity of the ball? And this is randomized, so I don't know if yours is going to ask for the same thing. But mine is asking for horizontal velocity graph. And I know that for any projectile, whether it's launched up at an angle like this or if it's launched horizontally, it doesn't matter. Horizontal velocity is constant. And so I need something with a constant velocity to the right, and it says here that the right is positive, so I need a constant positive velocity, and this is, let's see, going to look like this. Okay, this one asks which graph represents the vertical component of the velocity of the ball, and so let's see. If I look at this, I'm looking for the vertical velocity. Again, vertically, my velocity starts out upward and it ends going downward. And so it's going to go up and it's going to get slower and slower and slower. Right here at the top, we're going to stop for a split second and then we're going to go down and get increasingly faster. And so I need a velocity time graph that shows an initial velocity that is positive, but a final velocity that's negative. I have to cross the x-axis. And this is true for anything thrown upward in the air, whether it's a projectile that's also thrown forward or even something just thrown straight up. It's going to look something like this with a negative slope. The slope of that VT graph would, of course, be negative 9.8 meters per second squared. Question 3 says a projectile is fired horizontally to the north at a velocity of 18 meters per second. What is the horizontal velocity of the projectile after 4 seconds? So although this looks like a calculation, this is not a calculation, at least not the first part, because this is asking for horizontal velocity, and we just talked about this in the previous question, but the horizontal velocity of a projectile is constant. And so if it was fired horizontally at 18 meters per second, then it will still be moving 18 meters per second at every other moment while it's in free fall. So after 4 seconds, I would expect it to still be moving 18 meters per second to the north because it was to the north initially. This says what is the magnitude of the vertical velocity of the projectile after 4 seconds. This is not constant. I can actually set up a table similar to what I did in the other question a minute ago, and we can solve for this. You could also set up a table just to look at the pattern of the velocities. So if we want to set this up, again, we're going to need to keep our horizontal and our vertical directions separate. So I'm going to make myself a little T-chart for X and Y. And I'm going to be labeling my initial velocity, final velocity, acceleration, time, and displacement in this little table. And so this particular projectile I know is fired horizontally with an initial velocity of 18. I know its final velocity horizontally is still 18 because I know that I have 0 acceleration in the horizontal direction. In the vertical direction, because I have a horizontal projectile, I know my initial vertical velocity is 0. Again, you have to know that. You have to be able to fill that in. It won't be in the question. I know that my acceleration is due to gravity, negative 9.8. And I know that I'm looking for the magnitude of the vertical velocity after 4 seconds. So I'm specifically looking for at a time of 4 seconds. How fast it will be going vertically. And that's what we're looking for is vertical. So I'm solving for this, which means I can only use this side of my table. I have VI, A, and T, and I'm looking for VF. And if I look at my kinematic equations, I'm going to want to use this one. VF equals VI plus A times T. If I plug in, that's VF equals 0 plus negative 9.8 times 4. Okay, and so we're just going to multiply negative 9.8 times 4, which gives me a final velocity of negative 39.2 meters per second. It just wants the magnitude, so I'm not going to type the negative sign because it says magnitude right there. So 39.2 meters per second down because it will be falling. All right, question number 4 says, an arrow is fired horizontally at a height of 2 meters above the ground. A ball is dropped straight downward at a height of 2 meters above the ground. Ignoring air resistance, which one hits the ground first? If you have something fired horizontally and something dropped, and they're dropped or fired from the same height at the same time, they will hit the ground at the same time because, again, horizontal motion is independent of vertical motion. The fact that it's moving forward doesn't affect the rate at which it falls downward. And so let's see, they both hit the ground at the same time because gravity acts the same on both. I showed you guys a Mythbusters video in class where they did this with a bullet fired forward versus one dropped from rest at the same time. And they will hit the ground at the same time if they're at the same height and dropped at the same moment. Number 5, a projectile is fired at an angle of 58 degrees and travels a horizontal distance of 22 meters on Earth. Which of the following changes will result in the projectile traveling a greater horizontal distance? So here we're looking at what factors affect the range of the projectile. And this is something that we looked at in the PhET that we started our unit with. And so we have a situation with the projectile being launched. I'm just going to sketch this out at 58 degrees. And we know it's going to have some trajectory. It's going to land somewhere over here, wherever that is. Okay, you could certainly solve for it. You don't need to. Okay, we're just looking at this conceptually. But it's asking which of these changes will make it go farther? How can I get it to go even farther than where it's landing now? And so let's talk about some of these different factors. You can see here there are 3 different answers, all involving angles. And we talked about this in our notes, but the angle that's going to give you the greatest range, the one that's going to make it go the farthest horizontally, is going to be 45 degrees. 45 degrees will be farther than anything else because if you have something launched at 45 degrees, you have an equal amount of forward motion and upward motion. So you have the right combination of the two so that it gets high enough off of the ground, but also is moving forward with enough velocity to carry it even farther than 58 degrees or than any of the other numbers up here. So this would give it a greater distance. Making the angle even larger at 75 degrees, like something like this, would make it go a lot higher, but it wouldn't go farther. It would actually go shorter because it would go really high up in the air, but then it wouldn't have enough forward motion to get farther than this. So we're not going to select the first one. The smaller angle of 32 degrees. Again, smaller isn't necessarily going to be farther here. Yes, more of it's going to be horizontal, but you have to look at those angles and how far they are from 45 degrees. Okay, 58 is 13 degrees away from 45 degrees. Okay, 45 minus 13 is 32, which is the angle that's listed here. So this angle right here, this 32 degrees, will actually have the exact same range as the 58 degrees right here. Okay, because it's the same distance away from 45. So it would be launching at a smaller angle like this, which of course is more horizontal. Okay, but because it doesn't get high enough in the air, it's not going to go any farther. It's going to land at the same point. Okay, so the only angle here that would give it a greater distance is 45 degrees. Let's look at the other variables or options that we see. Increased mass. Mass has no effect whatsoever on the range of your projectile. Unless there's air resistance, mass is not going to be a factor that affects anything, just like it didn't affect an object's free fall. So we're not going to select this because it wouldn't give us a greater horizontal distance. It shouldn't affect the distance at all. Faster launch velocity, though, that absolutely would give me a greater horizontal distance. If I launch it faster, it should have even more upward and even more forward velocity if it's at a faster speed, and so it would end up farther away because it should end up going higher in the air and greater velocity forward. Again, these are randomized, so you're going to have different values or different answer choices potentially, but these two are going to be options that are going to give you a greater range. Other things that could result in a greater range would be if there was air resistance in this question, removing it. Getting rid of air resistance would give you greater range. Air resistance should reduce your range. But again, I don't know if any of the options have that as a choice, but if they do, doing this without air resistance would give you greater range. If you were to do this on the moon, you would have a greater range. With a smaller gravitational field, you would have less vertical downward acceleration, which would mean it's in the air longer and it can move forward farther. If you were to have launched it at some height, elevated it, also would give it a greater range. I'm trying to think if there are any other variables, but those are the ones that are coming to mind right now. Again, you may have different options on yours, but those would all give it greater range. And on mine, I only have 2 answers that would give it greater range. All right, question number 6. A projectile is thrown at an angle with a velocity of 22 meters per second. What is the vertical velocity of the projectile at the top of its flight? Again, this looks like a calculation. It's not. The vertical velocity of your projectile at the apex, at the max height, is 0. That's the point at which we're up here. It stops moving up so that it can start moving down. It turns around. And so you have a velocity of 0 meters per second at the max height, at least a vertical velocity. Horizontally, it's still moving forward, but vertically, 0. Does it have a horizontal velocity? Yes. It is equal to the horizontal component of the initial velocity because horizontal velocity is constant. So whatever portion of this was horizontal, you're still going to have the same amount. So maybe like 15 meters per second was horizontal. Well, it's still 15 meters per second at the top. It would be that speed everywhere. Last part of this says, what is the vertical acceleration of the projectile at the top of its flight? And again, that vertical acceleration is the same at every single point. It's not just at the top. It's negative 9.8 meters per second squared, or meters per second everywhere. Question number 7. A water balloon is launched at 56.9 degrees with respect to the ground at a velocity of 21 meters per second. Let's assume there is no air resistance during its trajectory. So this one's breaking it into parts for us to help us to solve it. Hopefully you already knew to do these parts because it shouldn't have to specify to do this, but it does, so it's trying to help you out here. So let's go ahead and sketch what we have. So we have our 21 meters per second launch at an angle of 56.9 degrees. And so because we're launched at an angle, we need to solve for the components. When you have something at an angle, part of it is horizontal, part of it is vertical. And you can solve for those parts. If this is 21 and this angle right here is 56.9 degrees, we can solve for the different components. We have our horizontal component, we have our vertical component. And we're going to use a SOHCAHTOA to do this. Okay, if I want to solve for this side, my y component, it is opposite my angle, and I have the hypotenuse. Opposite and hypotenuse are right here, so I'm going to use sine. And in this one, I would say that the sine of 56.9 degrees equals, and again, this is going to be opposite over hypotenuse, so opposite is y, hypotenuse is 21. So it ends up being 21 times sine of 56.9. Again, when you're doing this, you do need to make sure that you're in degree mode. If you're not, you're going to get the wrong answer. So 21 times sine 56.9 gives me a y component. I'm going to go ahead and type it in here instead of writing it, of 17.592. I'm going to keep at least 2 decimals on it because that's in my directions, meters per second. I'm going to do the same thing for this side. This side, though, is adjacent to my angle. Adjacent and hypotenuse shows up here in cosine. And so I'm going to have 21 cosine 56.9. And that's going to give me the x component of this. So 21 cosine 56.9 is 11.47 for the x component. Okay, part B, how long does it take the balloon to reach its peak? So now we're actually doing a calculation. I know that we found those components, but we want to go ahead and put them in the table. We can't do our calculations, or at least you shouldn't be trying to do calculations without labeling everything that you've been given. So I'm going to make a T-chart, VI, VF, A, T, delta X. We're going to go ahead and label some things. Again, when you do find the components, that's what goes in here. Don't put the 21. You're going to put the X component, which was that 11.47. You're going to put the Y component, which was the 17.59 as the initial. And we're looking for how long it takes to reach the peak. So I can look at this to max height, just like I can look at it to impact for the Y direction. But I'm going to go ahead and do to max height because it's asking about the time to reach the peak. Okay, and if I do that to max height, then I know my final velocity at max height vertically is 0. I also know my acceleration vertically is, due to gravity, it's negative 9.8. I know horizontally that my velocities are constant, so it's going to be the same, 11.47 meters per second, because my horizontal acceleration is 0. I don't have any other information, but what I'm trying to solve for first is the time. So we're going to look for the time to max height, and we're going to use the vertical data for that. Again, I'm using to max height here. If you use all the way to landing, you could add another column on and have 17.59, negative 17.59, negative 9.8. But if you do that, remember, you're going to have to take half the time at the end because we only want to max height, and that would be halfway through the trajectory. So if I do it this way and solve for it here, I don't have to do anything to the answer I get. It will just be my answer because I've already set it up so that I'm looking at max height, because that's where the velocity is 0. So if I want to go ahead and do this and solve for time, I'm going to use this equation, VF equals VI plus A times T. My final velocity is 0. My initial velocity is 17.59 plus negative 9.8 times T. And that's going to give us negative 17.59 equals negative 9.8 T. And then we're going to divide both sides by 9.8. Those negatives are going to cancel. And if I use the whole value that I didn't round, because I rounded that 17.59, if I use the whole thing, then I'm going to get a time of 1.795 seconds. And so that's what we're going to put here. How long does it take to reach the peak? 1.795 seconds. What is the maximum height reached? Again, because I'm looking for max height, this is what I want to use. Again, you're able to have another column here. We just wouldn't be able to really use it to find anything because it's specifically asking for max height. If I want to determine my max height, I need my displacement vertically. And so it's the only thing left to solve for. So you can solve for this with any equation that has delta x in it. So let's go ahead and use this one. It doesn't really matter. Delta x equals VIT plus 1/2 AT squared, where I have VI is 17.59. My time is 1.795 plus 1/2 times negative 9.8 times 1.795 squared. So that would be my setup here. I'm going to use the values that haven't been rounded so that I don't introduce any rounding error. And I got this as my answer for max height, 15.79 meters. All right, this is question number 8. It says, a catapult launches a water balloon forward on level ground with a velocity of 11.5 meters per second at an angle of 32 degrees above the horizontal. Assume no air resistance and that the positive directions are upward and to the right. So let me go ahead and sketch this real quick. Again, it's probably not drawn to scale or anything, but we're going to call this 32 degrees, and we're going to call this 11.5 meters per second. And so it tells us to fill in the table for the entire time in the air. So in the last question, I did it just to max height. This time I want to do it all the way to landing whenever I fill in the table. So it's telling me to do that as opposed to filling it in just to top. Again, if you have something launched at an angle, like I do right here, my first step needs to be to solve for the components. I'm not going to type 11.5 in here. Instead, I'm going to figure out how much of this is this way, how much of it is this way, because I have vertical and horizontal components here. And that means I'm using sine and cosine. This one's adjacent, so I'll use cosine, and I'll say 11.5 times cosine of 32, which is 9.75. Let me go ahead and fill that in for my horizontal. 9.75. My horizontal is constant, so I'm going to fill it in down here too, 9.75. My acceleration horizontally is 0. For the vertical, I'm going to use sine because it's opposite my angle, so I'm going to do 11.5 times sine of 32 degrees, which is going to give me 6.09 as my initial vertical velocity. My final vertical velocity, if it's launched upward with an initial 6.09, it will land with a downward or negative 6.09 meters per second. My acceleration vertically will be negative 9.8 meters per second squared. Okay, and so it wants us to fill in the entire table, so I do need to go ahead and solve for time and for displacement. I'm going to find time first because that one's a little easier. VF equals VI plus A times T. I have those numbers on my vertical side. VF is negative 6.09. VI is positive 6.09. So I have this, and so I'm going to have subtract 6.09 from both sides, and I'm going to have negative 12.19 equals negative 9.8t. Divide that by negative 9.8. The negatives will, of course, cancel, and my time will be 1.24. Again, I'm using unrounded values on my calculator screen, so that if you're wondering why 6.09 times 2 gave me that, that's why, because I'm using the unrounded value. Again, time is not horizontal or vertical, it's scalar, so I'm going to fill it in the same on both sides. There's no such thing as horizontal and vertical time. Vertically, my displacement for something that I launch from the ground at an angle and lands back on the ground is going to be 0. So I can fill that in vertically. Horizontally, though, it will land some distance over here, so I do need to find the range. I have everything else in that horizontal column except for range. So if I want to solve for range, let's go ahead and use one of our kinematic equations. I'm going to use this one. Okay, because if that acceleration is 0, that whole thing goes away, and displacement is velocity times time. That's my constant velocity equation. Okay, so we're just going to take our velocity, 9.75, and multiply it by our time. And again, that 9.75 was rounded, so I'm going to go back up and use the unrounded value, and I get 12.13 for my horizontal. And it asks for what is the maximum height that it reaches. So I actually didn't solve for that in my table. This was for the entire air time. If I want to find max height, that occurs right here at half my time. And so if I want to find this, I can't use 1.24 seconds. This value right here won't work. I need to use half of that. And so if I divide that by 2, I get a time for just the up portion of 0.622 seconds. That's half my time. And I can use this, and you can even add a third column on to do it to get to max height, but I can use this to solve for my vertical displacement. Okay, so if I use that time, I use my acceleration can still be negative 9.8, of course. My initial velocity, VI, is still 6.09. I can solve for delta y. And I can do it using this equation. Delta y equals VIT plus 1/2 AT squared. Okay. Okay, so let's go ahead and plug that in. Again, I want to use the unrounded values. 6.09 times my time, just the time up, plus negative 4.9, that's half of negative 9.8, times that time up squared. And that gives me a max height of 1.8947 meters. All right, question number 9 says a ball rolls off of a level platform at constant velocity and lands on the ground 2.8 meters away from the base of the platform 0.55 seconds later as shown above. Assume no air resistance and that the positive directions are upward vertically and to the right horizontally. Fill in the table for the entire time in the air based on the information from the problem description. So just like the last one, we have a table to fill in here for vertical and horizontal. So let's start with the information in the question. We know that it lands 2.8 meters away. It's in the picture. It's also in the question right here. And that is our horizontal displacement. So let's go ahead and fill that in. We know also that the time that it takes to land is 0.55 seconds. So let's go ahead and fill that in. And again, that's neither horizontal nor vertical. It's just time. It goes in both sides. I know that this is a situation where the ball is rolling off of a level platform that makes it a horizontal launch. So I know that the initial vertical velocity will be 0 because that's the case for every horizontal launch. I know that my vertical acceleration will be due to gravity, negative 9.8 meters per second squared, and that horizontally I don't have any acceleration. I don't know the height of the platform, so I can't fill that in. I don't know the final velocity vertically. I don't know the velocity horizontally. So this is all I know so far. The rest has to be solved for. So looking at this information, because I know both time and displacement in the horizontal direction, I can solve for velocity. My equation for constant velocity is the last of my kinematic equations, which says that delta x equals Vf plus Vi divided by 2 times time. Again, when I'm dealing with horizontal motion, because we're at constant velocity, these will be the same, which means that you can rewrite this as delta x equals V times t. And so that's what we're going to do. We're going to plug in our displacement, 2.8 equals V times 0.55, and we're going to divide both sides by 0.55. 2.8 divided by 0.55 gives me a velocity horizontally of 5.091, and that is the same for both the initial and final and for every point in between because we're at constant velocity horizontally. Looking at the vertical side now, I'm going to go ahead and solve for VF first, using, again, just the vertical data. VF equals VI plus A times T, because I have the other values. And again, this is just for vertical Y direction. So this is going to be equal to 0 plus negative 9.8 times 0.55, which will be negative 5.39. In the displacement vertically, the last thing I need to solve for, again, I can use any equation that has delta y in it. I'm going to go ahead and use this one. Delta y equals VIT plus 1/2 AT squared. Okay, so plugging in, that's going to look like this. VIT, that's going to go to 0 because the initial velocity is 0. 1/2 times negative 9.8 times 0.55 squared should give me my vertical displacement, which is going to be a vertical displacement of negative 1.48, which makes the height of the platform 1.48. It's going to fall by that distance because that's how tall it is. Meters. And then how does the momentum of the ball compare at these 2 points during free fall? So looking at the momentum at launch versus impact, at launch I have an initial momentum. Again, momentum is mass times velocity. So basically the mass of the ball isn't changing. I'm just looking at how the velocity changes or if it changes. And so it's going to start out with just horizontal velocity. It's still going to have the exact same amount of horizontal velocity here. However, it also has vertical velocity at the end of, again, negative 5.39 meters per second. So because it's speeding up as it falls, it's getting faster, it's also going to be gaining momentum. Therefore, the momentum at launch will be less than the momentum at impact. Question number 10 says, you fire a projectile on flat ground with an initial speed of 14 meters per second at an angle of 55 degrees above the horizontal. I'm going to go ahead and sketch that out first. Okay. Neglect air resistance. How long is the projectile in the air? Okay, so I know that this thing is going to do something like this. It's going to land over here. Okay, and we're just trying to figure out time, at least to start. So it's a good idea, as always, to start with a little chart to organize our data in the X and Y directions. VI, VF, A, T, delta X. So, again, if you have something launched at an angle, I'm not going to put 14 in here. I need to find the components. I have a horizontal component. Again, if you have something at an angle, part of it's horizontal, part of it's vertical. We need those two pieces. This is 14, these are not. And so we're going to be solving for them. This one we're going to use cosine because it's adjacent to the angle. This one we're going to use sine because it's opposite the angle. And so we're going to say that 14 times cosine 55 will give us this. Let's go ahead and do that. 14 times cosine 55 degrees. Again, make sure you're in degree mode. That's going to give me the x component, which is 8.03. Again, horizontally, it doesn't change. It will be the same the whole time. There's no acceleration horizontally. Vertically, again, I'm going to look at my vertical data to landing or to impact. I could also have another column here of vertical data to the max height. Okay, depending on what we're trying to solve for, that might be helpful. Either way, you can get the answers you're looking for. Okay, so if I want to find the vertical component here, again, I'm going to use sine since I'm opposite. 14 times sine of 55 degrees is going to give me 11.47 meters per second. And if I'm going all the way to impact, my final velocity here at the end, if this starts out with 11.47 up, it will end with 11.47 down. But if I was to do this only to max height, if that's how I'm going to write my table, depending on what we're solving for, you might want to try that. Then up here, my final vertical velocity is 0. Again, we really only need this column if the question is asking us for something about max height, like how high it went, or something like that, the work done as it rises up there, you know, whatever. So we may or may not need this column, but I'll go ahead and fill it in so you can see it. Again, vertically, my acceleration is going to be negative 9.8 meters per second squared, and that's going to be the case, whichever we're looking at, that's going to be the case. So that's the vertical to impact. Vertical displacement, if we launch and land at the same height, then we're going to go ahead and say that it's a displacement of 0. Okay, so we can go ahead and find the time right here, and that'll help us with each of these other columns that we have filled in. If I want to find this time, I'm going to go ahead and use this equation, VF equals VI plus A times T, but I only get to use numbers from this column. So that's going to be negative 11.47 equals 11.47 plus negative 9.8T. When I solve for that, that gives me a time of 2.34 seconds, which is the time here as well. But it's not the time here. Because we're looking only to max height in this column, that's only half the trajectory, and so it's also only half the time. So I'm going to take my answer and divide it by 2, and my time to max height will be half of the total time, which is 1.17 seconds. Okay, but this question doesn't ask for just to max height, it just wants how long is it in the air, the total. So let's go ahead and fill it in, 2.34 seconds. All right, next question says, what is the projectile speed as it passes through the highest point in its trajectory? So right here, I've already filled it in here, but vertically, it's not moving at all. It is still moving forward. And so if I want to answer this question, then we need to go ahead and just put in our horizontal velocity, which is going to be this 8.03, because it is still moving, it's just not moving up or down. It stops vertically, but it's still moving horizontally. So 8.03 meters per second. All right, the next part of this says, if the projectile has a mass of 0.208 kilograms, what is its change in kinetic energy from launch to max height? So kinetic energy is just going to rely on the resultant velocity, because energy doesn't have a direction. We don't have to solve it for like horizontal versus vertical. Energy is energy. It doesn't have a horizontal or vertical. And so I know my initial velocity is 14 meters per second. And I know the velocity up here. In fact, we just filled it in right here. But up here, my velocity is just the horizontal piece because it stops moving vertically. So this is 8.03 meters per second. So clearly I have a change in my velocity, and therefore I'm going to have a change in my kinetic energy. The kinetic energy equation, if you don't remember, is that KE, kinetic energy, is 1/2 mv squared. So we're going to solve for kinetic energy here, we're going to solve for kinetic energy here, and we're going to figure out what the change is. I know it's going to be a negative change because I slowed down, but let's go ahead and solve for it. So KE initial at launch is 1/2 times the mass in the question is 0.208 times my initial velocity, which is 14 squared. If I go ahead and solve for that one, I get 20.384, and my unit for energy is joules. KE final, which in this case is talking about at max height, because it's asking for the change from launch to max height, would be 1/2. Again, same mass, 0.208, but my velocity at max height isn't 14 anymore. It's just that horizontal piece because vertically it's not moving at max height. So that 8.03 squared. Again, I'm going to use the number from the calculator that hasn't been rounded, because 8.03 is a rounded value, but it's actually really close because it's 8.030070. So we'll see how close it is. But I'm going to go ahead and use that value, and that gives me a kinetic energy of 6.706 joules. And so if I'm looking for the change in kinetic energy, the change in anything, change in position, change in velocity, change in momentum is always final minus initial. So change in kinetic energy is going to be 6.706. That's my final KE minus 20.384. That's my initial KE, which of course when I subtract these, I'm going to get a negative number. And it will be equal to negative 13.678. And my unit will be joules. Oops, I did not type the negative sign. Okay. All right, the last question says, what force or forces is or are responsible for the work done on the projectile that causes this change in kinetic energy? So in other words, what force makes my kinetic energy change? Why does this slow down? And the answer to that is, of course, going to be the force of gravity. Because that should be the only force acting on a projectile is gravity. It says to neglect air resistance in the question, but again, if we have a projectile, we have been assuming this from the beginning. Otherwise, we wouldn't be able to use all these numbers over here. Like, I wouldn't be able to put that if there was air resistance, which would make it impossible for me to solve this question. So we've always been assuming no air resistance, therefore I'm not going to pick that. I do have gravity. The initial launch. Okay, yes, there is an initial force to get this thing moving. However, as soon as that hand or that slingshot or that cannon or whatever it is, as soon as it stops touching it, that force is no longer acting on it. Once it's in the air, it's a projectile. The only force acting on it is gravity. That is the only answer you should select. Number 11. All right, number 11 says a bullet is shot at 264 meters per second, straight left from a helicopter at a height of 529 meters. So I'm going to go ahead and draw a picture. Straight left, 264 meters per second, and we are going to be at a height of 529 meters. Okay. It says if it accelerates toward Earth for the whole fall, it will take t equals however many seconds before it hits the ground. So it just wants to find us to find the time. And so if I want to find the time, again, we can make a table here. We have initial velocity, final velocity, acceleration, time, and displacement. And we want to look at those values in both the x and y directions. Again, a horizontal launch is horizontal, so there is 0 initial vertical velocity. But my initial horizontal velocity is negative 264 meters per second because it's to the left, and it says here that the right direction is positive, so that makes the left direction negative. Again, horizontal velocity is constant the entire time because there is no horizontal acceleration because there are no horizontal forces. Vertically, I know that I do have acceleration of negative 9.8 meters per second squared due to gravity. I don't know what my final velocity is. I only know that it isn't moving vertically at first and it's going to accelerate for some amount of time to get to a faster speed. But I do know how far it's going to fall while that happens. Because it started out 529 meters high, the displacement vertically will be negative 529 because that's how far it has to fall to reach the ground. So from this information, I can solve for the time using my vertical data. I don't have enough information here. I can't solve for time without this. So if I want to find time over here, then I'm going to, I have VI, A, delta X, and I'm looking for T. I'm going to use this equation. Delta Y equals VI T plus 1/2 AT squared. Again, delta Y will be negative 529. That initial velocity vertically is 0. Remember, I'm only using numbers from this side. So that whole thing is going to go away because that's going to be 0 plus this. So I'm just going to write this part. Half of negative 9.8 is going to be negative 4.9, and then I'll divide that from both sides. That's going to cancel this, and over here, 529 divided by 4.9 gives me that 107.959 equals t squared. We're going to take the square root of both sides to get a time of 10.39 seconds. And again, that time we can fill into both sides of this table. Also, the bullet will have a horizontal displacement of blank when it lands, so it wants us to figure out this value now. Okay, again, displacement is velocity times time whenever we're dealing with constant velocity. And I can get that from this equation, delta x equals Vf plus Vi divided by 2 times t, because Vf and V are the same. If I add them and then divide by 2, it's just going to be velocity, so velocity times time. So if I want to find that displacement, I'm just going to take my velocity, negative 264. I'm going to multiply it by the time that I just found, 10.39, and I'm going to get a displacement of negative 2743.05. Again, this is actually the unrounded value, so let's fill it in, negative 2743.05 meters. Be careful with the signs here, because mine was shot to the left. I do have to put a negative sign on, but if yours is shot to the right, that's positive. You don't have to worry about the signs for yours. All right, the last question on here is a bonus question that I am giving you to see if you can figure out how to do it. If you look at the warm-up question that's posted for today, there is one similar to this, so I would encourage you to look at it, but let's go ahead and take a look at this one. It says, a toy catapult launches a 4-gram projectile at an angle of 30 degrees. So I'm just going to draw a picture. There we go. If the projectile has a total initial momentum of 0.0668 kilogram meters per second, what is its momentum at max height? So they gave me a momentum here, which I can't really fill into my table. However, I know that momentum is mass times velocity. And so because they gave me a momentum and a mass, I can actually use this information to find that initial velocity, and then I can use that to fill in my givens in my table and solve the rest of the problem. So the problem, though, is that when I use this equation, the masses need to be in kilograms, and they gave me a mass of grams in the question. So before I can do anything else, I have to convert that. There are 1,000 grams in a kilogram, so if you're trying to figure out how many kilograms this is, you need to divide by 1,000, and of course you're going to get a small number. But let's go ahead and plug in. My momentum is 0.0668, and it's going to be equal to my mass in kilograms, which is 0.004 times V. If I divide both sides by that 0.004, I can figure out what my velocity is. And that's going to be equal to 16.7 meters per second. So that goes here, because that's my initial velocity when it's launched at this angle. So that is that velocity there. It wants to know what its momentum is at max height. So of course it's going to have some trajectory that looks like this. And in order for me to find momentum at max height, I need to find its velocity at max height, which means I need to set up my table. So we're going to be looking for VI, VF, A, T, delta X, and we're going to be looking for that in both the X and Y directions. So plugging in. Again, this velocity is at an angle, so I need to solve for the components. If you have something launched at an angle, start by finding the components. I'm going to use cosine for the horizontal component because it is adjacent to the angle, and for the vertical component, I will use sine. So I would say that 16.7 times cosine 30 degrees is going to give me my horizontal component, that's x, that's going to be 14.46. For the y direction, same idea, but we're going to use sine, and that's going to be 8.35. Okay, if I'm looking for this point right here, I know that I'm looking at max height here, so I'm going to set this column up to solve for max height as opposed to the whole trajectory. And so that means at max height, my vertical final velocity is 0. So that means that my momentum at max height is entirely dependent upon how fast it's moving horizontally. And my horizontal velocity at max height is the same value it was here because acceleration horizontally is 0. There are no horizontal forces. The only force acting on this is gravity, which means that I have a vertical acceleration of negative 9.8 meters per second squared. But I actually don't have to do anything else in this table to answer the question of what is the momentum at max height. Because again, momentum is mass times velocity, and the velocity at max height is this. Okay, it's the same everywhere. And so if I wanted to solve for my momentum at max height, I would take my mass, which was that very small 0.004, and I would multiply it by the velocity, and it's just the horizontal component, 14.46. And we get a momentum of 0.05785. I'm putting several decimals. It says you need at least 3 significant figures. Those do have to be 3 correctly rounded significant figures. So if you wanted to, you could type 0.0579, or you can type more digits. Just make sure you round correctly. The last question here says, if the projectile is launched from the edge of a 1 meter high table, how far away will it land on the level floor below? Okay. So I drew this so that it's landing at the same height, but this question is saying, hey, it's not going to land at the same height. It's on a table, and it's going to keep going, and it's going to land somewhere down here, okay, if this is the edge of my table. Okay, so now there's nothing here for it to land on. It's going to go lower than where it started. Okay, so the way that you solve this if you're on uneven ground, and the warm-up question today has an example like this if you want to look back at it, but you have to solve to max height for this one. And you're going to have basically motion up to this point, and then you're going to have motion all the way down to here. So if we're trying to figure out how far away it will land, we're looking for the range right here. Then we're going to need to figure out how much time it's in the air for. And we can find the time up to this point. That's pretty easy because we have all the information here to max height. And then we're going to have to figure out the time to fall from this point down to whatever height it is, which is going to be 1 meter below where it started. So looking at this, let's go ahead and solve for the time just to get up to max height. We're going to call that time up. Okay, so let's find time up to max height first, and that's going to be using this data to max height. And so if I want to do that, I have VI, VF, and A. I'm going to go ahead and use this. VF equals VI plus A times T. Plugging in, that's going to be 0 equals 8.35 plus negative 9.8 T. Again, I want to use the unrounded values, although 8.35 actually isn't rounded. That was the exact value I got. But the time up is going to be 0.852 seconds. Okay, that's not my answer. That's just the time it gets up to here. Okay, I need to figure out how high this is so that I can figure out how high it's falling from. And that will give me the rest of the time that I need in order to figure out the total time in the air. And then from there, I can figure out the range that it would have. But let me go ahead and fill in my time up to my table right here, 0.852 seconds. So let me go ahead and find max height as well, because I need that. If I want to find this, I'm going to go ahead and use this equation, delta y equals VIT plus 1/2 AT squared. VI is 8.35. My time is 0.852 plus 1/2 negative 9.8.852 squared. and we get a height, max height of 3.5573, and that's rounded. But that's what we get to max height. Okay, so we have now figured out, we have this thing launched. I keep doing that and drawing it, like, I don't mean to draw that all the way. Do this, okay. All right, I know this is 1 meter high. Okay, I know that max height right there. I know that the time it takes to get there, time up, is 0.852. I know that this distance here is 3.56 meters. So I know that at the max height, it's not 3.56 meters above the floor, it's 3.56 meters above the table. The total height that it's at is 4.56 meters. So it has to fall from 4.56 meters to the ground below. And so if I'm looking for the rest of the time down isn't equal to time up in this case because I'm not on level ground. It would be if it were landing here. Okay, then I would say they were equal, but they're not. This time is going to be greater, and it's going to be the time it takes for it to fall negative 4.56 meters. Not just back to the table, but all the way to the floor below. Again, my acceleration is still gravity. I'm looking at everything right now in just the vertical direction. My vertical velocity at this point is 0. So that is going to become, for the second half of my equation now, that's going to be my initial velocity in the vertical direction. This is all vertical data right now. Okay, is 0. Okay, and that's helpful because I can solve for the time now, because I have 3 other variables, and I can do that using this equation. Delta y equals VIT plus 1/2 AT squared. That's going to be negative 4.56 equals, this whole thing's going to go away to 0 because this is 0. 1/2 times negative 9.8 times t squared. All right. So if I divide both sides by negative 4.9, that cancels all this. We divide that. Sorry, I just realized you can't see that. We divide that, we get 0.93 basically, but we need to take the square root. So t squared, 0.93, t is 0.9644 seconds. So that's the time down. Okay, time down. So now I have time up and time down. If I'm trying to figure out my horizontal range, which I was looking for all the way back up here, I need the total time that it's in the air. So we're going to take the 2 times that we just found, and we're going to add them together. Okay, and the total time in the air, which is going to be this time up plus my time down, okay, is going to be 1.816 seconds. That's the total. And that's what I use to find range. Range is going to be, again, if you have no acceleration, you have constant velocity, you're going to be using the equation delta x equals v times t, because I have constant velocity here. So if I want to find my range, I'm just going to multiply my horizontal velocity, which is 14.46, which I think is a rounded value. So let me go all the way back up in my calculator to find the initial value. And we're going to multiply that times the total time. which is what we got when we added our times together. And when I do that, I get this. So the range here, 26.27 meters. Again, this was listed as bonus because you're not going to have a question like that on your test, but I just wanted you to try it. So if you've solved this and you got it right, you will have a 105 listed up here as your score. If you guys have questions, please make sure that you ask them prior to your quiz tomorrow or your test on Thursday.